The most prevalent way that drugs act is by inhibiting enzymes to regulate key biochemical processes. Examples of these are numerous and include such things as the statin family of cholesterol-lowering drugs, inhibiting the enzyme responsible for the synthesis of cholesterol in the liver, thereby lowering cholesterol levels. In the fight against bacteria, the group of compounds known as the penicillins act to inhibit formation of the bacterial cell wall by inhibiting an enzyme required for that process. In this video, we focus on understanding the ways that enzymes can be inhibited by drugs by breaking into a few different classifications and looking at some examples of each. There are two main types of enzyme inhibition, and when we talk about drugs, the majority will fall into one of these two categories since most drugs act by inhibiting enzymes. The two types of ways that enzymes can be inhibited by drugs are reversible inhibition. That is the scenario where a drug comes in, binds to an enzyme, and ultimately the enzyme can regain activity, for example, when the drug is no longer bound to the enzyme. An irreversible inhibitor, in contrast, is one where the enzyme is permanently destroyed. In other words, it can't regain activity. One scenario in which this happens is with some chemotherapy drugs that form covalent bonds to certain R groups within the protein. Once that covalent bond is formed, that covalent bond to the drug can be considered permanent, and the function of the enzyme is permanently disrupted, meaning that the enzyme will not lose connection to the drug molecule, and the enzyme will be permanently destroyed in function. So these are going to be the two types of classifications that we can give enzymes, where we differentiate them based on whether the enzyme can ultimately regain activity. That's usually going to correspond to non-covalently bonded inhibitors that just come in and through electrostatic interactions or hydrogen bonding engage with the enzyme to interfere with its activity, versus generally the more nuclear option of irreversible inhibitors, which generally permanently link to the enzyme to permanently disrupt its activity. In addition to exploring whether a particular drug is a reversible or irreversible inhibitor, we can also look at whether drugs act competitively or non-competitively. Through the illustration that we see here, with a competitive inhibitor, what happens is that the substrate, which is intended to come in and bind at the active site for a reaction to take place, competes with an inhibitor molecule. Usually the inhibitor molecule has a structure that is somewhat similar to the substrate, so that inhibitor is able to bind in place of the substrate at the active site and hence interfere with the substrate in coming in and interacting with the enzyme. So in other words, the inhibitor is competing for the active site with the desired substrate of that enzyme. When developing competitive inhibitors, scientists have a variety of tools in their arsenal. Namely, we now have a lot of information about the three-dimensional structures of various enzymes, including understanding the shape of their active site. Hence, we can now design molecules that have structures that will be expected to be complementary to the shape of the active site, but which we would expect to bind to the active site, but for reactions not to be able to be catalyzed at that location, thereby allowing us to create a variety of different competitive inhibitors of enzymes. Competitive inhibitors are often useful, particularly in cases of competitive reversible inhibitors, when we don't want to completely shut off the function of an enzyme forever, but instead we want to control and limit its function. In the case, going back to the statin family of cholesterol-lowering drugs, we don't want to turn off the production of cholesterol entirely because cholesterol is a required biomolecule, but we want to be able to control how much cholesterol a person is able to produce, and hence things like competitive inhibitors typically work very well in those situations because the amount of competitive inhibitor can be fine-tuned to allow the body to have some level of enzyme activity without shutting it completely off. Non-competitive inhibitors are another route that drugs can inhibit their target. In this case, the substrate, as we expect, binds to the active site of the enzyme. All looks good and well there, but at a different binding site, referred to as an allosteric site, an inhibitor binds. What happens when the inhibitor binds is that that actually changes the shape of the active site, so the active site is no longer able to as capably bind to the substrate as it was prior to that non-competitive inhibitor binding. With the active site shape no longer optimized, the enzyme can no longer catalyze a reaction as effectively. We call this non-competitive because the inhibitor is not directly binding to the same location of the enzyme as the substrate. Instead, it's binding somewhere else entirely on the enzyme, but ultimately eliciting a change in the shape of the enzyme at the active site. As you might guess or imagine, these drugs are more difficult typically to design because rather than looking for a drug that will fit into the active site and be a competitive inhibitor, instead one has to look for a different location on the enzyme where one might predict that an inhibitor would bind and ultimately elicit a change in the three-dimensional shape of the enzyme. That is definitely not a trivial thing to do, making the development of non-competitive inhibitors relatively difficult. In the case of both competitive and non-competitive inhibitors, there are a variety of examples out there of reversible competitive inhibitors and irreversible competitive inhibitors. Likewise, with non-competitive inhibitors, those can also be reversible or irreversible depending upon exactly how permanently the inhibitor binds to the enzyme. If it binds permanently, we consider it to be an irreversible inhibitor. If it binds transiently, we consider it to be a reversible inhibitor.